Okay, now we're going to continue our discussion of the link layer protocol, continue our review, and we're going to talk a little bit about addressing. So previously, in the previous lectures, when we talked about the network layer, we talked about the concept of the IP address. Like we said before, the IP address is a 32-bit address that the network layer uses um, for addressing a particular interface, and it's basically used for layer 3 forwarding, basically forwarding IP packets through the network to get from the source to the destination. Um, in the link layer, we also have addressing. Works a little bit different, and it's basically called a MAC address. And our MAC address is basically also known as a LAN address or physical address, or sometimes called an Ethernet address. Um, and it's basically used locally to get a frame from one interface to another physically connected interface. So there's a physical link that you're going to traverse on, and that's what the MAC address is basically used for. So it basically call this link basically the same address, kind of map that to what we're talking about with IP addressing. And that might be more confusing than it needs to be. So as we go through this, you'll basically will understand the difference between MAC addressing and the higher level IP addressing. So now MAC addresses are basically, for the most part, hard-coded. They're 48 bits long, and they're usually burned inside of the NIC card's read-only memory. Sometimes they're also software settable. It used to be popular at one time for network administrators to set their own MAC addresses, but really that practice has kind of fallen out of favor. And basically, MAC addresses are usually represented in a hexadecimal or base 16 notation. So basically each number, and the numbers of course can go from 0 to F, each number represents 4 bits. So on a particular local area network, each particular adapter will have a unique LAN address, so also known as a MAC address. So basically, if you have a computer with more than one network adapter, it will have more than one MAC address or LAN address. Okay, it looks like I accidentally skipped an important slide here, so let's kind of get back to this slide. So here's another representation of MAC addresses as defined in the IEEE 802 RFC. So for all 802 networks, this is the MAC address format. So it's basically 48 bits, usually represented in this format. If we want to do send a broadcast MAC, we basically set everything to all ones, which would basically be all Fs in the hexadecimal notation. And basically, they're set up like this. So the first bit is either a 1 or a 0. If it's a 1, that means it's a broadcast or multicast. If it's a 0, it's going to be a unicast. The second bit is basically universal or local. Universal meaning globally unique, um, and 1 meaning it's assigned by the local network manager. So if it's a 0, it's assigned by IEEE. If it's a 1, it's assigned by a local network manager. But this basically has fallen out of favor, the idea of having a local network assign MAC addresses, so it's not really used anymore. So the only time this second bit is 1 is when you send out a broadcast address. The next 22 bits are what you call an organizationally unique identifier. So each organization that creates NIC cards has a unique identifier, and each of them are assigned the last 24 bits to make the MAC address a unique value. So I apologize. We already talked about this slide. Continuing on, so basically the MAC address allocation is administered by the IEEE. The manufacturer buys a portion of a MAC address, the MAC address space, to ensure its uniqueness. So you always have those first 24 bits end up being unique. So the way to look at it from a human point of view, a MAC address is like a social security number. So once you assign a social security number, it doesn't change. An IP address is more like a postal address. It's a place that basically belongs to you or is associated with you, but the IP address can change over time where the MAC address does not change. And the MAC address is no subnetting, it's a flat address space, and it's portable. So basically, if you move a network card from one local network to another, it's going to bring that address with it, so it's not network dependent. Whereas in comparison, the IP address is hierarchical, therefore it's not portable. The IP address depends on the subnet to which a node is attached. So if I move a node from one network to another, I have to change the IP address, but I do not change the MAC address. Just like if you change homes, you change your postal address, but you don't change your social security number. So one of the key concepts in MAC addresses is how do we determine an interface's MAC address knowing it's an IP address. And you do this using a protocol called ARP, or Address Resolution Protocol. Okay, so we know an IP address and we need to determine a MAC address. So what do? So let's kind of take a look at our example network here. So each of these hosts have an IP address, and you can see they're all in the same subnet, and you can see each of these hosts have a MAC address assigned. So at each host, each node, whether it's a host or a router, actually has to maintain an ARP table on the local LAN that it is connected to. And it basically has an IP at MAC address mapping for some of the LAN nodes. And these entries in the ARP table have the IP address, the MAC address, and some sort of TTL, or time to live value. Basically, these last about 20 minutes. And the purpose of this is it basically forces these entries to get updated so we don't have any old data sitting in our ARP table. So basically, we all start off, let's say you start off with you want to go to a web page. So you start off with, a host name, which is basically some sort of website. You need to resolve that to an IP address. And then when you send your data out, you need to go and send it out. Now basically, unless the web page is on your local network, you're going to send it out your next hop router. So you're going to at least have to have the, from the MAC address point of view, you're going to have to get that MAC address of that next hop router to get out off your local area network and onto that website that you want to get to. So that's why you have to do this resolution, this address resolution already down to the MAC address layer. I'm going to talk about this a little bit more, so if it's not making sense, it will as we go through. So let's talk about the situation where, okay, you just have a local network. You want to send data just on your local network between two hosts. Let's say you have a, let's say you're in some sort of lab facility and you have like a local client server, you're doing some local calculations. So your local hosts need to talk to each other. So A wants to send a datagram to B, and if B's MAC address is not on A's ARP table, it can't do that. So it broadcasts an ARP query onto that local network containing B's IP address. So it's going to have a destination MAC address of all F's. So that means that all the nodes on that LAN are going to receive that ARP query. So B, which is our intended destination, receives it because like everybody else didn't realize it by the IP address, hey, this was actually meant for me. So it replies to A with its MAC address. Then A will then cache it to its ARP table until that information times out. So we refer to this information timing out as being a soft state. So it goes away unless it's refreshed. And basically, the creation of the ARP table is automatic. It doesn't require a network administrator to go in and manually write the ARP table. This is basically done automatically behind the scenes. So that's nice, talking about a LAN connection. What about the more common connection of routing to another LAN? So you basically have A is on some network here, and it wants to get to host B on some other network. So basically you want to send the datagram from A to B. They're on two different subnets, so there has to be a router involved in between the two of them. So let's assume we're going to focus first of all on the IP datagram layer and the MAC layer, the frame layer. Let's assume we've done our DNS lookup and A knows B's IP address. Okay. And let's also assume that A knows the IP address of the first hop router. So it's going to know that either one of two ways, either through DHCP, that we talked about previously, or some sort of network administrator has hard-coded that information onto A. And basically we assume that A knows R's MAC address, and that's probably going to be because when the router came online, it basically broadcast its MAC address to everyone, so A probably already has that, and that's probably how it has that MAC address. So it knows how to get to its default gateway. It knows the correct MAC address. The only thing it doesn't know, it knows B's IP address. The only thing it doesn't know is B's MAC address. But that's not really relevant right now. So what's the first thing that's going to happen? Okay, so the first thing it's going to do, it's going to create an IP datagram with the source, its source address and the destination IP address. Next, it's going to create a link layer frame with R's MAC address as the destination and the frame that contains the A to B IP datagram. So why am I sending this to R? Because we just have one link. Okay, so link layer protocol deals with one particular link, so it basically cares about getting us from our host to the other end of the link, which would either be there's better be something on the local network. Since we're going off network, that end of the link is basically our first hop router or our default gateway. So that gets sent along. Okay, so now the frame has now received the R because it's destination. It's the final destination for that that link layer of datagram. So the datagram gets removed. It gets passed up to the IP layer. So now R, because of course R knows how to get to B's subnet. So now R is going to send the datagram with the source IP address A and the destination address B. But now it's going to put its source address as the MAC source address. Okay, we don't care about A because this is going to be a new link. Okay, because now this router is connected to this, in this example, this particular subnet. And so it has its MAC address as a source address. And it's going to put B's destination address. And basically this is the same mechanism. So here the router has learned all of the other hosts on this subnet. So it has an ARP table that has B's MAC address. So a new link layer frame is created with a different source and destination address, and this gets sent off to B. And so R forwards the datagram to B, and as you can see, it eventually gets to B because it has the final destination MAC address and IP address. So basically, this kind of shows how link layer protocol works. That the link layer frame changes every time you change links. So let's talk about the specifics in regards to Ethernet. Ethernet is kind of the most popular, most widely used LAN. So we're going to talk about Ethernet networks. So basically, many years ago, there were a lot of different local area network technologies that were vying for usage. There was Token Ring, FDDI, there was even ATM to the desktop, because ATM can be a local area network and a wide area network. But basically, eventually, Ethernet dominated. It basically dominated because it started off with the widest usage. It was the cheapest, and it because of its wide usage, there was a lot of research and development into improving its speed. So eventually, Ethernet was started off basically as a 10 megabit per second network that wasn't as fast as other technologies. It was slower than Token Ring, it was slower than FDDI, it was slower than ATM. It basically became a faster than all its competitors. So it was cheap and fast. So basically, Ethernet basically took over the local area network landscape. So let's talk a little bit about the physical topology of Ethernet. So in the early days of Ethernet technology, excuse me, Ethernet was pretty much a bus structure. So you basically had this coax cable with terminators, and you had these T connectors, and you would basically connect your Ethernet nodes into this physical bus structure. So basically back then Ethernet was very dependent on dealing with collisions, and that's where CSMA CD that we just talked about came into play. Today, pretty much all Ethernet, at least all wired Ethernet, is set up in a star topology. So basically, the Ethernet hosts are connected into a switch. Each spoke runs a separate Ethernet protocol, so basically there's no collisions that happen anymore when you're using a switch. Now sometimes you have an Ethernet hub. Basically an Ethernet hub is really just a collapsed bus, so an Ethernet hub and Ethernet switch are not the same thing. You can have collisions on an Ethernet hub, but even those have fallen out of favor because the Ethernet switches have become very, very inexpensive. So I think just for my own sanity, and we're going probably for yours as well, we're going to stop here, and we are going to continue by talking about the Ethernet frame structure.